Let's talk about magnetism. So we've mentioned it a few times, and you've seen it come up mostly in terms of when I write force electric, I do, is it QE? Yeah, probably. QV cross B. And every single time I've been like, well, we don't have a magnetic field or a moving charge. Sometimes we have moving charges. But I've said no magnetic field. And therefore that part goes to zero. Well, today that comes to an end. So I'm going to talk about what the magnetic force is. So first, let's talk about how this equation is used. And that's supposed to be a vector. So I don't know how familiar you are with cross products, but we're going to review that briefly. So let's say we have two vectors. So cross product is you take one vector, you take another vector, and it creates a vector that's parallel to both of those. So you can define any plane by two linearly independent vectors. And so when you do the cross product of those two vectors, what you do is you get a perpendicular vector that will then you can use those three vectors to define all of space. So without going too crazy, so let's say we have a vector like A and a vector like B. So we'll say A, B, and then we'll say A cross B. And the way I do this is take my right hand rule. I point my fingers in the direction of A, so it's A cross B. And so I then bend my fingers in the direction of B. So A cross B. I'm trying to do this really awkwardly because you really don't want that Roman salute, just A cross B. So in this one, so if A is that way, B is that way, then it's into the board. So A cross B in this case would be, I'll say C equals A cross B. A cross B then would be into the board, where by convention, you have into the board is like this, and then out of the board is like this. And it's like an arrow. If you have one of those old-timey medieval style arrows with, I guess, point, and then it's some sort of rounded arrowhead like this. If you see the arrow point coming at you, then that's going to be the vector coming out. If the vector is going into the board, you're going to see this back portion right here, which looks like that. That's not actually probably how the notation was originally devised, but that's the mnemonic for such. So another quick aside would be then, red, A cross B would equal negative B cross A. So B cross A would then be, let's see how it is. So it would be down and then cross B. So it would be B cross A. And then the resultant vector C, which is B cross A. Running out of room, awkward writing, would then be out of the board. So towards us. Similarly, the two vectors don't have to be perpendicular. But what happens then, so let's say we have purple. We're going to have a different B. So we have something like, pen, B, there we go. A cross B. So now we're going to do A this direction, and then B is just slightly off, but we're still going to have the same direction as we did before, even though they're not perpendicular. So the magnitude then is going to be the magnitude of A times the magnitude of B. Those little lines there, they're kind of like absolute values. They mean magnitude. Kind of like double absolute values. Magnitude. And that will equal whoop, 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 whoop. Magnitude of this equals magnitude of A times magnitude of B times sine of theta. So the mnemonic I use for this is, you would think that logically, well, this is a cross product, so it has to use cosine because they both start with C. Totally wrong. Human performance trap. That is trying to get you. That is a faux ami. Faux ami? Is that what the French say? A false friend? But the idea here is the cross product looks like it should be cosine. It is not cosine. It is in fact sine. So the magnitude is defined as sine. And one other way that you could kind of look at this is you can break down this b vector into, let's say, I'll call this by because it's kind of in the y direction, and I'll call this bx, kind of sort of in the b direction. And you could say that a cross b equals, let's see here, bx, a cross bx plus a cross by. And so what happens then is a cross bx is going to be a, change colors, bx, and then the theta between the two will be 0. And then therefore you have the sine of theta equals 0, and therefore there'll be 0 contribution due to the parallel component in this cross product. But then you'd also have a cross by, like this, a by, and then a cross by would equal magnitude of a times magnitude of by. So you can kind of think of it as only taking into account the perpendicular component of the a's and b's. So if you break down the b into parallel perpendicular components with respect to a, then you'd only use the perpendicular portion. And that's really what the sine of theta is doing. What it's saying is, for a cross product, the more perpendicular two vectors are, the more their cross product contribution is going to be. And it's going to be maximized when the two are perpendicular to each other. If you think of it like torque, I don't know if you've ever turned a stuck valve or really just like a nut bolt, really torqued it down, so to speak. What you're trying to, the best way to do it is you get your big bar, your wrench, and you're pushing it perpendicular to the moment arm, torque. And because it wouldn't make sense to turn it with a kind of funny angle and try and push it like that. So the idea is you want to get the most perpendicular action you can. And that has to do with the actual the formula torque, which equals R cross L, which is another instance you probably saw the cross product. So similarly here, you're going to feel more of a magnetic force when the charged particle is moving perpendicular to the magnetic field. Okay, so that is the formula for how you do look at the force. Now we're going to kind of sidestep a little bit and talk more about what's actually going on. So you've probably heard somewhere that the magnetic force doesn't actually exist. And that's totally true. Mostly true. I'm going to say it's true. So get here a line. There we go. Make it a thicker line so it's more accentuated. And we'll make it purple. We'll make it purple. Make a copy of it. So now this is more of a conduit. There we go. Maybe like that. Right there. Draw a little side over there. Ah, that's pretty good. Let's see here. Maybe something kind of like this to make it look like there's some perspective. Nah, I can do a better job. I can do better. Oh, there we go. A little bit of perspective. And so we have like a conduit, like a pipe. And in this pipe, we have a whole bunch of, let's say, actually, we're going to start by saying next to the pipe, we have a positive charge. Like so. And we're going to have a bunch of negative charges inside the pipe moving. hop, hop, like so, like this, moving this direction. There's also some over here. And we're also going to have positive charges. So this is, let's say, a chunk of copper, maybe? A copper bar, pipe. And so there are just as many positive charges as there are negative charges. But there is some charges that are flowing. The charges that are flowing are a relatively small amount because the sea of electrons, if you will, only comes from the valence electrons of the copper, and you probably only get one anyway. And so the electrons that are moving are a very small percentage of the total of electrons. And so you really have a very small number, proportion-wise, of total electrons moving. And so we have these electrons moving to the right, and we have a positive charge out here. Well, this is going to have to do with relativity. I don't know if you remember from previous physics, but the idea behind relativity is you have an underlying concept of relativity. It says the speed of light in every reference frame is about 2.99 times 10 to the 8th meters per second. More or less. A little bit more. And so what that's saying is, no matter how fast you're going, if you look at light, it'll always be going 2.99 times 10 to the 8th meters per second faster than you. This would be equivalent to saying that the speed of a car is 30 miles per hour faster than you. So you're like, well, if I'm driving 60 miles an hour, how fast is the other car going? Well, it's going 90. If I'm going 90, it's going 120. And it's using light, basically saying light will always, in every reference frame, no matter how fast you're moving, will always be going 3 times 10 to the 8th meters per second faster than you. And there are two consequences of this which are kind of interesting. One is the idea of time dilation, where faster you move, closer to the speed of light you get, faster you move, the slower time will be for you. So if you put a clock in an airplane, you fly the airplane around the world a few times, you look at the clock with another clock that you had, they won't match anymore. This has always become kind of a trope in science fiction, where they have some sort of great war and this great general, but then they have another war coming up in 1,000 years, and they're like, oh, what are we going to do? Oh, no. Well, we'll put him on a spaceship, zip him around for 1,000 years, and in 1,000 years, when this big fight comes, we want our super awesome general guy. Well, now he's only like 10 years older. And that's the idea with time. I know, greatly oversimplified. I don't care. The one that matters for us is another consequence, which is length contraction. The faster you go, the more length contracts. So if you see something moving, you have a person here, and he sees something moving this direction, it will appear to contract. I say appear, but it seems to be really does contract. The difference between theory and reality in this point really is a finer topic than I can really address appropriately. So as things move forward to an observer looking at these sort of things, it will contract. So then this gets down to the question of, it's like, well, you have a 10-foot garage, you have an 11-foot car, and it's like, well, can I park my 11-foot car in my 10-foot garage? And the answer is yes. Yes, you can. You just have to go really, really fast. And you can't stop. Which kind of defeats the whole purpose of having a garage in the first place. But yes, you can. The factor you hear of gamma, which is basically the factor of time dilation or length contraction, and it's going to be based on how fast you are going with respect to the speed of light. So it will be 1 over the square root of quantity 1 minus v over c quantity squared. And so the idea is, if you're going at the speed of light, then you have c over c squared, which is 1. 1 minus 1 is 0, and therefore time stops for you. The same thing with length contraction. This would be the amount of length that you see something else, or turn it over. You turn the fraction over, so that you would get something like the length observed is whatever your initial length would be times 1 minus v over c quantity squared, square rooted. And therefore, if you're going at the speed of light, you get 1 minus c over c squared over square rooted. So this would be 0, and it looks like you've shrunk, contracted down to 0. And then you have variations between 0 and completely shrunk. Okay, so that's the idea behind what we're doing here. As things get faster, they contract. So we have all these electrons in here, and as they're moving, they are also contracting. So these electrons, they go from spaced out like this to something like, ooh, I think I'm going to copy and paste this. Copy, paste, shrink, shrink like so. And so when there's no current flowing, there's no charges moving from one side to the other, there's no effect on this positive charge. But as soon as the electrons start flowing, they contract, or appear to contract. As far as anyone can tell, they contract. And so, since the negatives are moving, the positives aren't, we now have a region of space where there are higher density of negative charges than positive, and then there is a force on the positive charge towards the wire. And so you have this pull towards the wire from the moving electrons. Now, one of the other things you probably should remember is that you really only had to worry about relativistic speeds when you're talking about like 10 to the 5th, 10 to the 6th. So when you're solving projectile motion, there's a couple of like spider senses you should have in life. So if you can answer like 4 times 10 to the 10th meters per second, you're like, probably not. No, because 2 times 99 times 10 to the 8th, or almost 3 times 10 to the 8th meters per second is the speed of light. You can't go faster than the speed of light. Therefore, that's probably the wrong answer. And you probably forgot a square root somewhere, and maybe it's 2 times 10 to the 5th. And you just kind of wing it, and sometimes you're right. Also, if you got an answer like 6 times 10 to the 6th meters per second, you start having to think about, okay, this is getting into the realm of it's close enough to 2.99 times 10 to the 8th that I might have to take into account relativistic speeds. But other than that, the Newtonian approximation of relativity doesn't exist. It's usually pretty good enough. Now, the issue then with this is like, okay, so these electrons must be moving crazy, crazy fast. Well, that's the interesting part is not really. So I think this is called like drift speed. Just a sec, I'll find it on the Wikipedia. Whoop. Clickety clack. Drift speed. It sounds like a Fast and Furious movie. Actually, that'd be a great crossover. Someday when I'm rich and famous, I will do a Fast and Furious parody called Drift Speed. Thank you, Crystal Light. Okay. Numerical example. So, all right, drift speed. Drift velocity is the average velocity attained by particles such as electrons and material due to an electric field. Numerical example. Copper wire, check. Density, okay. Atomic weight of, okay. Copper has 1 free electron per atom. So, what is the atomic? Atomic weight is 63, so they have about, what's the, Okay, so they have these many electrons, and then they calculate how fast each electron is moving for, what did they say with the, for 1 amp? do some calculations, dimensional analysis. I love dimensional analysis. It's kind of the way of getting the right answer with having zero knowledge. Therefore, wires electrons are moving at 23 micrometers per second. That is slower than 23 meters per second, which is not even that fast when you're talking about relativistic issues. So this is saying that's really slow. Reason I can walk faster than that pretty easily. So the idea here is these electrons are not moving very quickly at all. And even though they're moving slow, there is 8.5 times 10 to the 28 electrons per cubic meter. Okay, cubic meter is a pretty big piece of copper, but you still have a lot of electrons in that wire. And you have so many electrons that even though this relativistic effect is almost negligible, it has a huge impact when you're talking about this many electrons. And so even though the electrons are moving slowly, they have relativistic effects, and you see that as the magnetic force. So the magnetic force does not exist. It's just a form of the Coulomb's law, electromagnetic force. I'll say electric force, electrostatic force, electric force. It's all the same thing. But it works differently enough, and it'd be so much of a pain to go through all the equations to basically convert static electric force to a magnetic force that it's like, let's just pretend the magnetic force exists, and it'll make all of our calculations easier and how do we intuitively interact with the world. So you're correct. The magnetic force does not exist, but let's pretend it does. And we go from there in life. So that's a little bit of background about the magnetic force. You will probably not be tested on that in any way. But it's good to have that sort of intuitive sense about what's going on. Quick. Okay, that looks good. So now we're going to go into some more of the practicalities of what we do or how we interact with magnetism. Whoop. Let that get deleted. Leave this formula up here. So with the electric force, we had two ideas. We had Coulomb's law, which was force equals Q over R squared. And then we had Gauss's law, which, let's see if I can remember it. It's going to be embarrassing if I don't. Equals, was it Q enclosed over epsilon naught? Yep. Oh, probably should put in some. And we have a dot product here. And then, as I said, Q over 1 and 2 over R squared. And there's probably like a R hat direction there. Okay. We have two kind of similar laws in magnetism, Biot-Savart and Amperes laws. It's good to see them work once, but for the most part, you really don't need them for this class. You don't need it for this exam. So I'm going to go through a couple of examples each just to kind of show how they work so that if push came to shove, you could look at the formula and kind of make it work. But I would not recommend memorizing these, nor would I recommend really having any fluency in them per se. So I think you're even given these two. Let us check. So these are the formulas you're given: mechanics, electromagnetic. Yep. So right here, this is Amperes law, and this is the Biot-Savart. And they look intimidating, but they're not that bad. So we'll start with Amperes law, and we'll use that to derive the magnetic field due to a wire. So there's basically four equations, four, that you should know with regards to magnetic fields. So you should know for a line, you should know the magnetic field due to a line, magnetic field due to a loop at the center, and a loop at some z above the center, and then you should know the magnetic field for a solenoid. or inductor. Are there two I's there for a solenoid? Maybe. I'm going to keep putting two I's there. Probably is in some language. So Amperes Law is, let's see here, I think it was on a closed loop magnetic field integrated by dl equals I enclosed over mu naught epsilon naught, mu naught. So I just don't like the way I drew that I. There we go. Let's check real quick. Back to our formula sheet. It's on top. Outrageous. Well, I guess that's why they give you the formula sheet. Whoop. Okay, red times mu naught. Okay, so what we're going to do then is we have a straight line of wire, like so, and there is a current running through this wire. Whoop, whoop, whoop. I going that direction. And what's going to happen is it's going to generate a magnetic field. So the rule of, we use the right-hand rule for this. Right-hand rules are really good for cross products. And so the way the right-hand rule works for this is you have your wire with a current going that direction. You put your thumb along the direction of the current, and then the direction you wrap your fingers will be the direction of current flow. So current going this direction, right hand, put the fingers wrap around, and so the current will go, the magnetic field will be this way, and it'll be circular. So if you look at this one, magnetic field here passes on our side of the wire, goes back, passes on the back side of the wire, and then loops around for a current going that way. But that doesn't tell us the magnitude. We'll use the formula to derive the magnitude. So the magnetic field at some distance r, I'll use little r, is going to be constant. This equation really doesn't show us that, but it is. And what's going to happen is we're going to have a uniform, so we're going to have dl, which is, it's kind of like a Gaussian shape, except I don't know if it is technically, yes. It's just a loop. We have a circle, and a small section length of this will be dl. So the magnetic field will always be tangent to the length. Tangent to the shape, tangent to the circle. So I'm going to take this circle and flip it normal-like. So it looks like this. Here's our wire. Here is a small unit of length, and that's also going to be the direction. So if we have the the current coming towards us, then the magnetic field would be going this direction. No, that one's wrong. There we go. And so the magnetic field and the length would both be going that way in this drawing. And so at every point, the magnetic field and the length will be parallel. And by being parallel, the angle between the two, theta, will equal 0. So for this dot product here, we can rewrite this as B dl times cosine, because dot product is cosine. It would make sense for cross product to be cosine, but it's not. That's a trap. Cross product is sine, therefore dot product is cosine. But we know that this is cosine is 0, which makes cosine of theta 1. And so we move to the equation of B dl equals I enclosed mu naught. And now that we have this, we can see that the magnetic field B is constant along this circle. And so we can pull it out. So we got B dl equals I enclosed mu naught. Now, even though the magnetic field is constant, we don't really know what it is. So, blue. So this is just the length of the circle. So this will be 2 pi r. Rewriting the equation, we get B equals I enclosed mu naught over 2 pi r. So the mnemonic that I use to remember this, and this is something you're going to have to memorize, is you have a wire going like this, with a current going that way. The magnetic field will be a circle around it. Using the right-hand rule, laying your thumb along the line of the wire, pointing in the direction of the current. And since it's a circle, it makes sense that there would be 2 pi r in the bottom. It's like, oh, there's a circle, there's 2 pi r involved, everything makes sense. Now that is 100% just mnemonic, because I haven't talked much about this mu. That's just 4 pi times 10 to the negative 7. So when you write in the 4 pi times 10 to the negative 7, the pi's cancel out, and you're not left with any pi at all, which is a disappointing fate to be in life. But the idea that you have 2 pi r on the bottom, when I see that equation, helps me memorize that, okay, that's due to a line because the magnetic field is a circle around the line. Just a mnemonic helps me memorize it. So this is the magnetic field due to a line. Go over here, clean up the board real quick. Do I have any equations that I like to keep? I will keep this one. Move you over there. I will add to it my magnetic field due to a line equals mu naught I enclosed. So basically the I, the wire, over 2 pi r, where r is the distance from the center of the wire that you're looking at. Okay, now I'm going to erase these. And that's how you use Amperes Law. So next we're going to go on to the Biot-Savart. I assume it's Savart. So bio, I think it says that way because I think it's French. And you say I's as E's, and the T is at the end, so it's silent. Maybe it's Biot-Savart? Maybe. I don't know. Probably not important. Okay. So now we're going to look at a loop. Specifically, we're going to look at a loop kind of like, I'm going to draw it like this. So we have a loop with a current going this way. And the way to find the magnetic field at the center is, again, the right-hand rule, except this time your fingers go along the loop in a circle, and your thumb will show you the direction of the magnetic field. So you're going to get something kind of like this for the magnetic field. And then it'll kind of zoom off towards the edges. But along the center line, it'll be straight. And then the question is, how do we find what that magnitude of the magnetic field is going to be? And we're only going to worry about the magnetic field along this center line here. So erasing this, redrawing it partially, and I'll try and do a better job drawing it this. That's good enough. Like so, like so. Nope, I'll leave that second one away. And we're going to look at magnetic field along Z. We're going to have, I'm going to say a radius R, and then we're going to have another radius here that we're going to call little r, because we have a current going along this loop here. But what we're really looking for with the Biot-Savart law, which I should write that up. Good point. Okay. Can I remember it? I think it's something like dB. I do not like orange for writing. We'll go to purple. So dB equals, I know there's a cross product. That's okay, I'm going to go straight to the sheet. Okay. mu naught I dl, mu naught I, I'm going to write dl like this, cross, I think, r, and it's r unit vector direction. So it's not the full vector r, it's a unit vector, so it's just telling you direction, not magnitude. 4 pi and r squared. 4 pi r squared, where the r is this r right there. So it looks fairly intimidating, but most things here are constant. So we know that mu is just 4 pi times 10 to the negative 7th. We have I, which I made it look kind of like a backwards 7 that's underlined, which it's not. It's actually supposed to be just an I. It's the current of the loop. dl, this will be dl right here. And in this picture, dl is actually coming out of the board towards us. And then r is up this direction. So this is the direction of r. So the first thing we should probably do is find the cross product of L cross r. This is supposed to be a vector. And I think we probably get a vector out of this too. I don't know. Probably. Because we have a cross. Okay. Focus. Focus. So L cross r, if we look at that, so we're going to have L going this way, but then we're going to cross it r going that way. So it looks like the magnetic field will be that way. L cross r. Yeah, I'm good with that. Are you good with that? I'm good with that. So we're going to be perpendicular to both of them. So we're going to have magnetic field in this direction. So this is where a little bit of your creativity is going to have to come into play. So we extend this line. We extend this line. We probably have a theta right there. And so this is going to be 90. This angle will be 90 minus theta. Zoom in. This angle then will also be 90 minus theta. This angle here I think is 90 degrees. Yep, that's 90, that's 90, that's perpendicular. And so this angle will be theta. And so as L goes around the circle, it's going to create like a cone of magnetic fields. So the magnetic field will point kind of like in a cone shape. And all of it will cancel out except for the vertical component. So this will be, I'm going to call it B net. So whenever you get a contracting gig and become a superstar in Hollywood, don't focus so much on your gross pay, focus on your net pay, because that's what you end up with to take home. Well, and taxes. But the point is here, I'm just trying to explain that net is the resultant after everything is canceled out. So the net magnetic field will be upwards. And so looking at this from our L point of view, this is so messy. I know, I'm sorry. I am sorry. So this is our theta. We're concerned with this one that's adjacent. So cosine of theta equals SOHCAHTOA. So we have adjacent over hypotenuse. So we're going to rewrite this looking for the magnitude as equals mu naught I delta L dl times cosine of theta over 4 pi r squared. And then I dropped this r because I already took into account its direction. And since it's a unit vector, it adds nothing to the magnitude. Okay, so now I'm going to erase most of this abomination up here. Oh, that worked out surprisingly well. Maybe erase some of this. And there we go. Put our Z back. So this is the Z distance that we're trying to find the magnetic field from the center. And now we need to find cosine theta. So I'll do cosine theta equals, as we said earlier, adjacent over hypotenuse. And that comes from SOHCAHTOA, which you should have learned a few years ago, many years ago. And in our case, the adjacent will be big R, right here. And our hypotenuse will be little r, which is big R, hypotenuse is little r. And we know that little r will be big R squared plus Z squared square rooted. So I'm just going to write to the 1/2. Okay, so rewriting this one more time. I say one more time as if I'm not going to do it again, which I probably will. I do DL. I know my notation is terrible between deltas and D's. It's okay. It is okay. Then we have big R over R squared plus Z squared to the 1/2. We still have 4 pi over here. And then we have an R squared, which I'm going to rewrite as R squared plus Z squared to the 1/2. But then I'm going to leave it as 2 over 2, because that way it'll be easier to combine these two in a sec. Okay. Mostly good. I am happy with most of this so far. Mu naught I R over 4 pi R squared plus Z squared to the, that's supposed to be a 2, but now it becomes a 3/2 integral DL. So I could take all of those outside of the integrand, because these are all constants. So the R is a constant, the Z is a constant. The only thing that's really changing is the delta L going around the loop. But going around the loop, the radius is going to be the same. The distance to this point at distance Z above the loop will be the same. Everything else will be the same. And so we can factor everything out. And then this becomes integrating. So this portion right there is just the loop, which is 2 pi big R. So we have mu naught I 2 pi, I'm going to call this R squared, 2 R's, 4 pi R squared plus Z squared to the 3/2. Do some canceling. Cancel. 2. Okay, that was not as much canceling as I had hoped for, but it is the appropriate amount. And so we write this. Okay, this will probably actually be the last time I rewrite this. B loop at Z equals mu naught I R squared over 2 R squared plus Z squared to the 3/2. Now you're probably thinking at this time, it's like, oh, that's so complicated. A little. I wish it was simpler, but it is not. So this is something that's probably worth memorizing, even though it is more complicated than things I like to memorize. The way I memorize things is I just grab a piece of, A4, 8.5 by 11 printer paper, and just write it over and over again until it is ingrained in your soul. And when I'm doing that, I feel free about, I write it down once, and then I basically write it down again and again, looking back at my original, and I keep doing it again and again until it's easier for me to write it down without looking at the original, where if I look at the original to copy it, it feels like that's just a waste of time looking at it, and it's easier for me just to write it down. There's no good way of memorizing things. Wow. There are better ways than others at memorizing things in life, but I hate memorizing. And I'm sorry that I'm asking you to do this, but it should be done for this test. But one of the bonuses is, I said one of the other things that you need to memorize is for a loop with it at the middle. Whoop. So I'll draw a real circle this time. Whoop. Professionally done. And so we know the magnetic field at the center of a loop is going upwards, but we don't know the magnitude. Well, if you memorize this equation, then you're also going to come across loops more often. We're looking at for the magnetic field at the center, not at some distance above the center. And the value of this is you can simplify this one with just z equals 0, and that'll give you the magnetic field for a loop. So you have something like r squared plus 0 to the 3/2, because you're saying z is 0 for the loop. The squareds cancel out, and so you get cubes, and then you get mu naught I r squared over 2r cubed goes away, and you got mu naught I over 2r. Kapow! Yes! And this is also worth memorizing. So, well, memorize the loop at z, and then be able to quickly simplify to the loop with z equals 0, and be able to recognize it. The mnemonic I used for the line was you're going to have a circular magnetic field. And that's the right-hand rule. Lay your thumb along the current and wrap your fingers. It has circular, so you're going to have 2 pi r. While the loop, again, just a mnemonic, it's going to have a straight line magnetic field through there, so you're not going to see 2 pi in the denominator. And that's the mnemonic I use for recognizing line versus loop. Yep, looks pretty good. No, one other formula that I will leave you with before, and I'll give this pretty much without justification, is the magnetic field of a solenoid. So a solenoid, like a loop, so a solenoid is just a bunch of loops on top of each other. When I draw it, it's like, I don't know. So draw a solenoid kind of like this. So you see loops, and there's a core. And that's, so the current goes like this. So your first thought might be, well, we'll just use the same for a loop, and then just multiply it for each number of loops we have. Well, that's not quite the way it works. So some of the complications you have with that is, with a loop, the magnetic field at the center is straight, but if you veer off the center, it's going to kind of flare out. And one of the ideas with a solenoid is it has a uniform magnetic field throughout. And that's an approximation, but it's usually pretty good. And so there's some different things going on there with a loop, but you're going to have the same general form as you will for the magnetic field for a loop as you do for a solenoid. So for a loop, you have mu naught I, check, you have those, and then n for the number of loops. But then you're also going to want to divide by L, which is the length. There's some approximations involved here. You're going to want to divide by the length of the solenoid. So that if you have a very big solenoid, it's going to detract from how powerful a magnetic field is. And so you want very tight loops of wire. Yep. Sometimes you'll see this written as mu naught I Ni, where n is assumed to be the linear density, which is just number of loops divided by L. But I like this way of drawing it out a little bit more because it feels more obvious to me and harder to make mistakes. So these are, so I guess maybe 5 equations you need. I know it sounds like so many. So you have your equation for force, electric. So you have QE, QV cross B, which we've written a million times, so that one should be kind of recognizable. And it's a cross product. You also have the magnetic field due to a line. So you have a line like so, and you have a magnetic field going around it. Use the right-hand rule where you place your thumb, direction to current, and your fingers wrap around the magnetic field. Your fingers would then wrap around and represent the magnetic field. The loop, where it's at Z, but I'm going to talk about just this basic loop first. So a loop, you wrap your fingers around the direction of the current, and your thumb will point in the direction of magnetic field. And then for a loop at some height Z, it flares off a little bit and it gets weaker, and you get this r squared over r squared plus z squared quantity to the 3/2, which you can then use that to simplify to get your loop. This is worth memorizing though. And then you have it for a solenoid, which is just a whole bunch of loops wrapped against each other. You probably did the whole thing. We made an electromagnet out of a nail. And that gives you a electromagnet. When you have a core, this assumes no core. Core basically is like that the nail. If you took the nail out, the electromagnet would still work, but it works better with the nail in it. And that is represented by this mu naught. If you have a core in it, basically like iron, then you would have mu instead of mu naught, and that there would be a unique variable, I'll call it whatever, some sort of factor that applies, makes it more efficient, that you just multiply then by mu naught. So you have a factor that you can look up. I don't know if it's a K or if it's a mu something. Meh. Iron, core, more efficient. So that mu naught right there can change a little bit depending on which application you're talking about. But the general formula for a solenoid will be mu naught times number of loops times the current going through divided by the length of the solenoid. So we'll do a couple more lessons on magnetism. There's a lot of problems here, which once you go through them, you're kind of like, okay, I see where this is going. But it's kind of an interesting combination of formulas and intuition, and that's one of the reasons why you see so many questions about magnetism on the AP exam. All right, that's probably good enough for now because we went over a lot. Didn't feel like it? Maybe it did on your side. On my side it did. I enjoyed every moment of it. But that's a lot of information. We will continue on with some problems next time.